Okay, so I just want to point out that this week is based on ANOVA, and not just ANOVA, but trying to determine why you would use ANOVA in comparison to something like, like pairwise t-tests or even the moods test. So there are different situations in which you would use different tests, and it's important to scan your data to know when you would use each one. All right, so let's go back to our trusty empty cards example, because it turns out it has a whole bunch of features that it makes it so I can kind of use it to interweave the ideas in the course. So I'm going to, in particular, pull out a couple of features. So you can see that here's the data set. And so far, we've been working a lot with the weight class. So if you scan the entire data set, you can see that we've used a lot the WT, which is the weight variable. And now that's because we haven't really been doing comparison along more than two groups. And the last time we did a comparison, we looked at VT, or we looked at VS, right? So we looked at the weight in conjunction to VS. And I think VS is referring to the shape of the cylinder. So now we're gonna look at something where we have three different groups. And if you can see that we have three different groups in the cylinder class, right? So there's 4, 6, and 8. And to kind of elucidate that, I kind of, I'm going to remove the help, I'm going to remove the dash so I can look at the help of empty cars and show you what we see. So if we look at the help of empty cars, you can see from this area here, right, that a cylinder is a discrete variable. And in fact, it has 3 different classes, right? So I could actually just, as you can see, that it's number of cylinders, and there's actually 3 of them. And in fact, maybe if we do something like, let me see, as dot factor of cylinder, we can see how many classes there actually are, right? So if we just run this, you can actually see that, oh, I have to actually attach it first, that's why. We'll see there's actually 3 classes, right? So this is, oh, I have to attach. So this is a lesson, like if you don't attach, even though this is a data set that's within the base R environment, if I don't attach it, I can't actually, it won't be able to read the cylinder variable. Okay, so you can see that there's 3 different levels. So again, what happened was if I don't attach the data frame, even though it's in base R, it doesn't read the variables itself. So you can see there are 3 different levels, 4, 6, and 8. Now the immediate issue here is that if I want to do any kind of discretization of this variable, because they're numerical values, the instinct is going to be for it's going to be for R to actually start taking averages. So I have to actually literally state as dot factor, so that in every analysis I do is that it knows not to actually average them out, but to see them as different levels, right? So this is what I'm going to do over the course of the actual tutorial. So this is obviously the number of cylinders, and then that means that a car can have 4, 6, or 8 cylinders. And this is going to influence, the question is, how does it influence the way of the car? So I'm going to use tidyverse, of course, and I'm going to put the best course of action before you even do any kind of ANOVA is to look and see what you have. The reason being is because I want to assess, right, whether or not my weight is differing across the different groups. Now, the immediate issue you have here is that so far we've been doing comparison across 2 different groups. And if you're thinking along this line, you're probably thinking to yourself, well, okay, comparison across 2 different groups, can I do the same thing with multiple t-tests across 3 different groups? And the issue is that you run into problems basically, right? So before we even elucidate why we cannot just use the pairwise t-test for the, for more than 2 groups, let's first see what we have when we compare our different groups. So you can see that if I don't put as dot factor across a cylinder, it won't actually run. It will just aggregate, it will just see it as if I'm taking it will remove the dummy variable. In fact, we can actually see what happens. It's a very interesting thing. It doesn't read it as a factor and tries to do some kind of funny thing. So this is the kind of work you see that it kind of doesn't like it. So just puts them all together as one group and takes a grand median. So you have to be mindful of this. If your data set kind of gives you have something that's actually discrete but numerical, you need to put as dot factor, or else it won't actually make any sense when you're looking at your box plot, and it will literally tell you, did you forget a group, right? So when you put as dot factor, recognize you have 3 different groups, because it doesn't look at them like numerical values, it looks at them as categories, which is what we want, right? So you can see here that you have outliers in group 8. This is something we should be mindful of, but more to the point here is that we're going to, tell ourselves that if we want to evoke ANOVA, we're assuming a couple of things. One, that our data is obviously normally distributed, but apart from the normality assumption, we're also assuming that the spread across the different distributions is the same. And so that means we have to ask ourselves, right, like if it's not true, then is this test appropriate, right? So we're assuming we have independent normal data and each has equal variance. Now, we could obviously see from the get-go that perhaps the spread of group 8 outliers aside is more compressed than what you see in groups 4 and 6. This may pose a problem with the assumption of equal variances. And more to the point, the normality issue may be something we question because obviously there are outliers in group 8. But let's pretend that we don't notice this and run our ANOVA test and see what we achieve, basically. Right? So because I have more than 2 groups, I'm thinking to myself, I should perform ANOVA. Now, suppose your first instinct was to say, well, you have 3 different groups. 3 different groups means you have 3 factorial different tests, but in fact, 2 of the tests will be the same. For instance, 4 and 6 is the same as a test between 4 and 6 is the same as a test between 6 and 4. So I'll divide the number of tests by 2 so that I don't get 2 permutations that are really the same test. And so you're looking at 3 different tests, right? So I'll repeat this again. Your idea one would be, let's perform a bunch of t-tests across each of the different pairwise comparisons while you have 3 groups. So 3 factorial divided into the fact that 2 permutations are the same yields 3 tests. So then you think to yourself, I could just perform a bunch of tests. Does anyone know what the issue with performing these tests are? Just out of curiosity, like in theory, it seems as if we should be able to take a t-test between 4 and 6, right? And then 6 and 8, and then 4 and 8. And see that the p-value is less than 0.05 at each of 3 different groups or 3 different tests. Does anyone know what the problem is with these like blatant comparisons across different groups when the groups are more than 2? So if you're making a comparison against more than 2 groups, does anyone see what the issue is when you perform this test? When you have this many groups? There's no like shame in giving an answer. Just out of curiosity, like have you guys thought about why like you cannot just perform blindly a bunch of t-tests across the groups? Okay, so maybe it's a bit early. The issue is that yeah, so the issue, that's okay, Ken. So the issue is that sometimes it takes you have to hear the ideas more than once to sink it in. So I kind of did a little bit of a math thing for you. I'm going to I did a code here because we're writing reports, right? So in some ways I kind of structured this so that you can kind of knit it yourself to PDF and then see how the report looks. So I'm going to actually show you guys how it looks, right? So I'm going to pull up the file and give you kind of a quick mathematical justification as to why there's an issue, right? So if I pull up my PDF here that I've knitted from, you can see that the issue is this. Okay. Typically speaking, you reject the null hypothesis if you have a significant test, right? So, and you guys tell me if at any point this is not clear to you, so I can go back and explain it again. You reject the null hypothesis when you have one significant test, right? So your p-value is, okay, so at least one significant test in all your bunch of tests, right, is equal to, well, 1 minus the probability of no significant test. This is a complement rule, basically. Either you have at least one significant test or you have none, basically, right? Now, having no significant tests is literally going to be the complement of having an alpha, one is going to be complement of 1 minus alpha. Why is that? Because alpha is a probability, right, that you reject the null hypothesis, given that it's actually true, right? So this means that no significant result here will be a complement of 1 minus alpha because alpha is a significant finding, basically. Right, so I'll repeat again, at least one significant result is a complement of none, basically. This is a probability theory, just complementation rule. And then no significant result means that, technically speaking, your alpha is bigger than 0.05, basically. So it's 1 minus your alpha, basically, but I took my default alpha to be 0.05. Right? So in this way, you have 1 minus 0.05 to the n. Now imagine, this is something that in the geometric series, you know that this thing is actually less than 1. And when you take it to the power of n, a geometric series will converge basically. So we'll go to 0, right? Because it's going to converge something that's finite. Now in the sum, basically, the sum will converge something finite, which means that the actual terms itself goes to 0 in large N. This means that with probability 1, if you take your N to be infinity, you're going to find at least one significant result, even if you truly don't actually have a significant result. So because these are all independent, so the reason why it's 1 minus the power of N is because each of these significant results, there are N tests to perform basically, and they're all independent tests, right? As in the comparison of group 4 and 6 is completely independent of the comparison between 6 and 8 and 4 and you know, like, and 4 and 8, etc. Right? So each of these tests are independent. So it's to the power of N, just literally multiply the product. And obviously it's the complement of having a significant test. It's 1 minus whatever your alpha is. That's going to be 0.05, which means that being that this is a series, with probability 1, the term will actually, this whole thing will go to 1 because this term will converge to 0. Right? So you're going to find at least one significant test, even if you truly don't even have a significant finding. So even if your results are not significant, with probability 1, if you take your N to be very large, where N is the number of tests performed, you will find an effect, even when you should not have, basically. Right? So, and this is because each test is independent. And when you perform a bunch of these independent tests, right, you will eventually find some kind of significance. So this is a problem, basically, right? So it's problematic that you perform, just because of the nature of how many tests you performed, you're likely to find with probability bigger than 0, you know, some kind of significant result, even when you should not have, basically, right? So, and this probability of finding at least one significant result will increase with the number of groups you actually have, because when you have more groups, you have more tests to perform based on the pairwise comparisons, right? So here, because our number of tests are actually only 3, we have a 14% chance of finding a result when there really actually is no significant finding, which is still not trivial, right? Imagine being told that you may have actually goofed and you found a 14% probability of something there, when in fact there is not, right? So, but this is growing for sure in N. If, for instance, I have, let's say, 10 groups, you can imagine that the probability of finding a significant result is almost close to 1, basically, right? So this is why we cannot perform multiple pairwise t-tests, right? So if your groups are more than 2, you ought not to do pairwise t-tests. So is this clear to people as to why we cannot do it? This is really the rationale as to why ANOVA became a thing in conception, right? Because we realized that with probability 1, we were going to find a result, even if there was none. And then if you're going to find a result every time, there's no point in even performing the test, right? Because you're always going to find something, even if it's an artifact. So this is why we needed to have a different test to adjust for this problem, basically, because if you perform too many tests, you have a chance of finding something. So this is why we use ANOVA. And in particular, ANOVA gives us a way to determine if we have any group difference at all, because instead of looking at the actual mean differences, it looks at the variance between the groups. So the ANOVA is different because it's literally an analysis of variance. In contrast to the t-test, which is looking at difference of means, you're looking at a difference of variance, basically. The idea is that you want to see whether or not the between group variance, that is the way the groups differ from each other in their variability, is it bigger than the variance you see within the groups? So if we go back to the actual table, you'll see that what we're actually saying is that we want to know whether or not the variance we actually see between each of these medians. So is the median here bigger than the median here, bigger than the median here, or is it that there's so much overlap between the groups and the variance is so wide within each of the actual bins that we can't see a between group difference, right? So we're always looking at the ratio of, the within group variability you see in each particular class that could actually, in some sense, overlap, obscuring the actual between group differences, or if you could actually find a difference between the actual groups by way of their medians, basically. Now you can actually see here there's little overlap. So the extent to which you actually see like a variability that's too big within the groups is probably not as severe here. But you can find pathological instances where your actual distributions overlap so substantially so that even if there is a difference in the medians, it's obscured by the overlap of the box plots, basically. So this is what we're really referring to when we say the analysis of variance. Does anyone know what the caveat is with this, though? There's a caveat here, right? So while it's in some sense improved, because instead of looking at instead of looking at the median differences and performing too many tests, we look at the overall grand variances between the groups and we assess if the p-value is small. Does anyone know what the issue is with this test, though? Like what the obvious issue is? Like what does it not tell you immediately? It gives you some kind of difference, but does it tell you everything? What do you not get from this test? Does anyone know? Like there's something that's missing, right? So we get that there's some kind of difference, but it doesn't really tell us, you know, where the difference lies, because all it tells you there's some kind of difference. But if you want to know exactly where the difference actually happens to sit, you have to do more work. So you don't actually get the full picture from just performing the test. It just tells you if there is a difference, the p-value will be less than your alpha, right? Telling you that there's a difference somewhere. But if you have more than two groups, you don't know where the difference actually is. So you didn't actually get the full picture. You have to do a little bit more work, basically, right? But anyway, this is why the hypothesis is set up in the following way. Instead of actually saying beta not, instead of saying, you know, the null hypothesis mu is equal to whatever, or mu is less than whatever, instead you say at least one mean is different from the other. So now we don't have a way to assess, right? Where the difference actually happens to sit. We're just trying to see if there's a difference at all anywhere, basically. And so this is the caveat here. The drawback is that you don't get the complete picture. And if you want to address where the difference happens to actually be with statistical significance, you have to move further than the ANOVA test, right? So let's see how this means be very explicit. In your reports, you know, be very clear as to how you are framing your null and alternative hypothesis, which, by the way, should be the first thing you actually elucidate. Before you begin the statistical analysis, make sure you make it clear, right, what the null and alternative hypothesis is, and then move to the question. And we'll just kind of add this in here. Okay, so I'm going to call it cylinder.ANOVA. Right, so this is the function. Again, I'm putting as dot factor because if I don't, since the cylinder classes were like 4, 6, and 8, it will take it as numeric, and this won't even run. It will tell me that I don't have different classes. So I put as dot factor so that it recognizes there are different group classes, right? And then I put summary. So let's see what we get. Okay, so what's the conclusion from looking at this table? Does anyone know? Like, am I going to actually reject the null hypothesis by looking at this table? What's the p-value that you guys see? There are no like, well, there's no like, yeah, there's no like shame in answering wrong. Yeah, exactly. 1.0 to the -6. Now, notice that you literally have two different classes. You have the residual sum of squares errors, right? And you have the betweens. This is actually the treatment effect here. The as dot factor cylinder is a treatment effect. The residuals is here. And so what it's saying is that this is the ratio of the two things. You can see that the sum of squares for the as dot factor is 18.18. The sum of squares for the residual is 11.50. So what it's doing is it's taking the ratio of this mean squared for these two things, because obviously degrees of freedom for as dot factor, because you have three different groups, is k minus 1, which is 2. And then you have n minus k minus 1. So this means n is 32 minus 2 is 30 minus 1 is 29. So this is why you have this thing, right? So just kind of, obviously, you know, your degrees of freedom, you know, call it between, is going to be equal to k minus 1. And then that's obviously 2. Then degrees of freedom within. So the within is the variability you tend to see within each group is n minus k minus 1. And so that's why you see what it looks like. And then that means that it takes the actual ratio. That's why you see 9.088 is taking the ratio of 18 divided by 2. And then here it's like 11 divided by 29. So this means that this blows up the ratio a bit, because obviously this is less than 1. So we'll blow this up a bit. This is why you see 22.91. And you can see that the result is significant. Now, because they have literally aggregated here, all the data is aggregated basically. You don't know where the actual difference is. So to Ken's point, right, you know, we will reject the null hypothesis and conclude that there appears to be a significant difference. Looks like I can't spell this morning. Between the cylinder classes at the 0.05 level, since, you know, our p-value is, of course, less than 0.05, which is equal to alpha. Now, here's the issue, right? I'm going to actually put this into math mode because I feel like I should be a bit like I can give you as much as possible for your report so you kind of know how to mimic stuff in terms of the math notation. Okay, so this is the caveat here. I didn't get which groups are different. So the extent to which so the question I asked you guys next is that, is this all we have to do, or like, are we done? Right? Well, the answer is obviously no, we don't know where the difference is basically. Okay, so that's why we have the Tukey's HSD. Tukey's HSD actually uses some kind of Bonferroni correction, which will take your p-value to be a function of n. So if you perform more tests, the tests become more, the actual p-value becomes, sorry, the alpha you actually compare your p-value to becomes more conservative, right? So the test in general becomes more conservative because your alpha level drops. Instead of looking at alpha of 0.05, you look at an alpha of like, you know, alpha over 2 to the n, right? So this, and so it's alpha over 2 to the n means as your n is getting bigger, in fact, your p-value is your p-value that has to be that much smaller to satisfy the criterion, basically. So that's what is going on there, right? And it will adjust in such a way that you can't just literally take the pairwise t-test at face value, because then you get some erroneous issues with your p-values. Okay, so let's do the Tukey's HSD and see what we get. I noticed I took Tukey's HSD of my actual model, right? So cylinder, not an AOV, it's Tukey's from my actual model. So what do we actually see here? Notice that you got a whole bunch of comparisons here, right? So it's comparing multiple things, right? So not only do you get a really cool, not only do you get a bunch of intervals, which are pretty cool, because you can then see here the duality between the p-value and the confidence interval. So some of you in your assignment too, you wanted to use the confidence interval approach, and that's fine. But the issue is that you first need to actually state that there is a duality between the confidence interval and the p-value, and that you would say something like, you know, we know that when we want to perform a hypothesis test, the confidence interval gives us a range of plausible values as to where the parameter happens to sit if we actually sample many samples of size n. Right, so this means that if our interval does not contain the parameter we hypothesize, we're going to reject the null hypothesis. So if you say something like this, then you could perfectly use the confidence interval as a hypothesis test. Why is that? Because you will see that for the p-values that are less than your alpha level, 0 would not be inside the actual interval for the lower and upper interval. Why is that? Because this is a difference of means. So of course, you're going to be assessing whether or not the intervals are far from 0, right? So that obviously we're going to question. So we want to know, we would like to know whether or not our intervals are far from 0, basically, right? So i.e. a significant mean difference, right? So because if 0 is covered inside the interval, if the interval covers 0, then you don't necessarily have confidence, because 0 then is a plausible value. You don't have enough evidence or confidence to reject the null assumptions. This is why we have to assess these things, right? So this is the caveat here. Okay. So cool. Any questions about this so far? Okay. So you can see here that what we have is a bunch of these comparisons. And in fact, we have them between, so the first interval is between 6 and 4. Then the next one is between 8 and 4. Then we have 8 and 6. So what you actually get is the actual difference you saw in the data. So this is the actual difference you observed in your data between the means. So when you subtracted 6 minus 4, you got a positive difference of this. When you subtracted 8 minus 4, it was even bigger. And then 8 minus 6 is this. So then these are the intervals we constructed. And it's kind of funny because the p-value is actually smallest in the middle here. That's because it's very far from 0. Whereas the other two are kind of, you can see the p-values are kind of, it's definitely, you're going to definitely reject the null hypothesis with these p-values, at least the alpha is equal to 0.05 level. But it's not as convincing as the difference between 8 to 4, which actually makes sense, because if you look at your actual box plot, you can see here that actually 8 is very far from 4 in terms of the mean. So it makes sense that it has the biggest group difference, right? Now the question is, before I ask the following questions, are we done? I'll say that you can see that all of the Suki's HSD test will actually yield higher p-values than any individual pairwise t-test you perform. So what I mean is that if you actually just take a pairwise t-test and examine the p-value you achieve under these t-tests, they will actually be lower, right? Because you haven't adjusted for the actual fact that you performed too many tests. So you should check and see. And by that I mean, like, just have a look and see, use the t-test function, right? And check and see. So for each of the 3 differences, you'll actually see that the p-value will yield something that is smaller than what you got with the Bonferroni correction, basically. So this is a real salient problem that goes back to the idea that if you perform too many tests, you're going to eventually get to with probability 1 from the math we showed here of seeing a significant result when in fact you did not have one, right? So we need to be mindful of this. This is why we're going to obviously make this correction. You can actually check and see how pervasive this can be by having to look at your t-test function to see what comes up, basically. Okay. So this is actually not 7, this is 8. Okay, so from the output, we can see that obviously all the differences are significant, but we particularly see that it's actually salient and in the difference between 4 and 8. So the question you could ask yourself is are you done, right? So, and I have asked this twice now. The first time I asked, are you done, was when we performed the ANOVA test at all. And I said, hey, you found a difference of groups, are you done? And then we kind of said, well, we haven't checked to see where the difference is. And now we have. And we see the difference are actually in all the groups. So you can ask yourself, are we done now, right? And you're still not done, right? Because I performed this test under the assumption that I could actually, right? So I assumed that I could do it because all the assumptions were satisfied. But should you feel confident to assume the assumptions are satisfied? I'm not entirely sure that you should, right? We need to check. We need to check in particular 2 things. We need to check if the data is actually normal and if we actually have equal group standard deviations. And I actually did bring this up in the first time around when I said that I'm not sure that I actually have equal group standard deviations, right? Because we could see that group 8 had the most compressed variance, even if we had outliers at the top. So, this alone should make us question whether or not, because this ANOVA function, be mindful of the fact that this ANOVA function in general is assuming equal variances. So there's another ANOVA function that you could use if you truly actually don't have equal variances. So we have to check this assumptions, basically, right? So I'm going to, you can see from the box plot, obviously, that's one way of looking if you have normal data, but I like to look at the QQ plot because sometimes the box plot and even histograms kind of obscure the evidence when your data is small. When your sample size is small, you get some weird things happening. So I like to look at the QQ plot just because sometimes checking whether or not your points tend to line is easier in some sense than, looking at visual descriptors with very small sample sizes. So I'm going to run this. So again, make sure you put as dot factor of cylinder, like CYL, or it won't actually make sense because it thinks it's numerical. So you can see that it actually partitions, it takes them as categories instead of numerical values. But does anyone see a true issue with one of the data sets? I would claim that probably the data set that's most mimicking the normal data is the data set 4. But did anyone see an obvious problem with one of the data sets? There's one that has a really serious problem. Does anyone see which one it is? Yeah, there's something wrong with 8, basically. We have so many outliers that were in our box plot that are now showing up as well in our QQ plot, right? So this is a huge issue because we have used this assumption of normality. And now we have to ask ourselves if we truly actually have normal data. Like you have these 3 salient outliers that in some sense obscures the true shape of your distribution for 8. So we only have 32 data points. So whether or not you want to remove those data points is questionable, right? Because when you remove those 2 data points, you then end up with 29 data points, which is suspicious. So then you really can't guarantee any kind of normality assumption because you're no longer even at the 30 sample size, right? So we're not necessarily inclined to remove the outliers just yet because of the sample size issue, right? And even before you move outliers, you should do some exploratory analysis to make sure that they're bad outliers. But yeah, we're slightly shaky, right? Because we're not too thrilled with what we saw in box in the QQ plot for 8. Right now, there's also quite a bit of spread because you can actually from the steepness of the steepness of your actual QQ plot gives you information too, right? So to me, it looks like it's steepest and in fact even highest in group 8 in comparison to group 4. So you don't even have equal. So this is kind of an issue. This in terms of the actual. Sorry, the steepness, it's actually less steep here, right? So it's less steep here. It's steeper in these 2 plots because I suspect the variability is bigger in those 2 plots. So it's less steep here. And that also gives you some kind of information as to the shape of the actual, the spread basically of your data. So the spread is actually bigger in 4 and 6. You can see it in the steepness of your actual plot, but you can also see it like in your box plot here, right? So this is something we're kind of looking at. And yeah, we can alleviate this in a couple of ways. So the thing is that you guys learned the moods test, right? So this means that if you truly believe that you don't have normal data, you shouldn't even really be using ANOVA's Welch test. So he taught you guys ANOVA's Welch test, which is what you use for non-equal variances, right? But when you use ANOVA Welch test, you still have normal data. It's just that you don't have, the issue is just the actual, the spread, right? But the thing is that if you don't even have normal data, you should ask yourself if it's even appropriate to use it at all. And then you would use the moods test. So if you suspect that the mean is very bad guess due to outliers, you probably should use the moods test, right? So the ANOVA is still, technically speaking, looking at the variance with respect to group means. So if you truly have some really bad suspicions about the normality of your data, you shouldn't really use the mean as a measure of the center. Then you should move to moods test, right? And so I suspect, I have some suspicions that I probably shouldn't use, right, ANOVA, but I'm going to use it anyways. I'm going to use the Welch's test just for illustrative purposes because I want to show you guys, and I already showed you guys moods test last week, but I suspect for this particular data set, I might think to use moods test, and you could obviously you could check yourself, right, as an exercise, just because I don't think I would necessarily feel comfortable assuming, just pretending this wasn't there. But I'm going to pretend that it's not there and use the one-way test. So you don't actually need this package. So this MR plus is actually not necessary for the one-way test. This is a built-in thing in R. But the issue is that you need it for this Games-Howell test, right? Because you needed to, it's almost equivalent to kind of a Tukey's test, but for Welch's ANOVA when you don't have equal variances, and this function is inside this package. So when if you do your reports next when it comes out this week, I think, and you suspect that you have normal data, your data is like normally distributed, that you truly don't have equal variances. So I'm going to put this here, normal data, but the variance is not equal, right? Then you can use this test here. But if you don't even have normal data, you probably should go back to the first scenario here, which is the moods test. Which that's the situation. It's like if your data is normal, move to Welch's test. And if your data is normal and you have equal variances, you use the ANOVA. If else you have like something that's like normal, but you don't have equal variances, use the Welch's ANOVA test. Else you use like moods test, right? So that's the order of the operations when you're scanning for what test to use according to your data. So now let's perform the test and see what we achieve. So you can see here that what you get is a p-value that's actually smaller than the p-value you got before. Notice that the test went down from 22 to 20.249. And you also got a p-value that's like down, that's like bigger as well. Before it was like, 1.07 to the -6 as Ken had. Now it's 1.963 to the -5. And so you can see your test is slightly less significant because you're adjusting for the fact that you have this, this different variances, and it's going to adjust the degrees of freedom and everything according to this. But it's still significant, right? So this means that now you've been told that there is some groups that are different. Otherwise, if there was no groups that are different, your p-value is bigger than 0.05, you stop the test and you're done. You just conclude they're all different. But now you need to use a James-Howell test. So I'm going to do that. And it looks a lot like what you do when you put the two keys, except the function is this instead of two keys, right? HSD. So what do I get when I do this? You can see that I get this weird table, right? So how is this be read? Notice that there's a dash here for 6 and 6. That's because you're not going to perform a test of 6 in itself. That's the same group. So that's why there's a dash there. But the p-value between 4 and 6, for instance, is 0.0042, which is significant. So it's saying that the significant group difference between 4 and 6. There's also a significant group difference between 4 and 8 because you have it to the -6 effect. Also, there's a significant group difference between 8 and 6 because it's 0.0049, which is certainly less than 0.05. But the difference you're actually seeing is most salient again between 4 and 8. And this is a staying thing. You can see from the graph that it's true, right? But you can see that they're all, the test is saying that they're all still significantly different from each other, right? So the only way to determine if you really feel comfortable with this conclusion, at least for me, if I was going to work in this data set, I would have to probably go back and perform the moods test, just because I was doing it for illustrative purposes. But certainly, if you look at my if-else statements, I didn't think I had normal data, right? So if it's the case that you have normal and equal variances, use ANOVA. If else, you use like ANOVA Welsh, but I don't even think I'm there either because I still don't think I have normal data. And so I'm going to go to the moods test when I don't have any normality. And I think that all my assumptions are off basically. Then I wouldn't want to center a test around the mean basically. So I would use the moods test, right? Any questions about this? So how does p-value compare? Obviously, it's going to be larger for a reason, right? So if there's no questions about this, I want to kind of just give you guys a brief overview in regards to writing reports, right? So the thing you're going to see if you look at Ken's slides is he does put the slides here. So please have a look. But the issue, the caveat here that he kind of elucidates is that this is for this report, this example he gives you in terms of how to structure your report is for a t-test, but you can still use it for ANOVA in the sense that you just have to change your ideas to represent the test you're actually working with. But what is really important in writing reports? Communication. Please, please, please make sure your grammar is complete, right? So this is where you can be penalized for things that are not grammatically correct or things that read poorly, for having really exaggeratedly big. If you have font that is exaggeratedly big, it doesn't look, 12-point font, are you within the margins? Are you saying things, communicating in a very nice way? You will see marked reductions there in your work basically, right? So it's not enough to obtain your data and do a suitable analysis. Even if you have beautiful plots and all your statistics was correct, and then when you got the last part where it says communicate your findings to the world and it wasn't coming across clearly, it's still not enough basically, because no one's gonna be able to read your analysis by itself. It has to come together with what you're saying basically, right? You need to be able to communicate and convey your findings adequately, right? So this means that this is twofold. One, your ideas are, your grammar is obviously you're writing grammatically, but also you conveyed your ideas beyond the scope of just your data analysis. You did not just say, reject null hypothesis and conclude this. You conclude it within the context of your data. You maybe gave a couple of reasons and a couple further context as to why you think the findings turned out the way they did, or what is interesting about your findings that you saw. Like you gave us some extra insights that you didn't necessarily have to, but you did because you wanted to communicate or sell your ideas basically, right? Because you know, a lot of times when you want to publish papers, you need to convince your audience. And, you know, something I learned myself as a grad student, I need to convince not just myself, but those around me that, in fact, the paper I'm writing is making any sense, right? So it's not enough for me to say, look at what I found, this is awesome. You know, it has to be the case that they also think it's awesome. And if they can't understand what I'm saying, it's not going to be awesome to them, right? So communicate your ideas is perhaps the most important part, as Ken is saying, because it's how we know, you know, like what you're saying is in some sense eye-catching, right? But there is a logical, apart from like good writing, you know, like you do want to explain, if you make a conclusion for a hypothesis test, you may want to explain why you think your results are the way they are, basically. So this is what he means when I say provide a complete and concise explanations, basically, what your results tell you and why. So you can make a conclusion about your hypothesis test, but give us a couple of sentences to why you think the test is or is not surprising in terms of the findings, why you think maybe the test came out the way it did in terms of its findings, right? You want to make sure that you are giving some additional insights into your ideas, basically. Now, here is the actual structure. You guys, or you may or may not have seen this before. You have 4 components: the introduction, the methods, analysis, and resulting conclusions, right? Now, introduction is kind of you telling the reader your problem, right? Don't just plunge into your problem. First, give a couple of sentences as to why your problem is interesting, right? And once you have done this, then you might want to provide some context of the statistics you're going to perform to obtain the statistics you're going to perform to actually, you know, like answer your question. So you're going to do a t-test. Well, in this case, you're going to do an ANOVA test, right? To address what you want to actually show people. So the objective has to be very clear and salient. In addition, you need to actually tell people what you're going to do to bring forth the answer to the question you want to address, basically. So first, set the tone with the opening sentence, and, you know, open the problem. Then give enough, you know, that's what it means, like provide enough explanations to what you're trying to do. Then give a framework to the statistics you're going to perform to actually do it. I'm going to do an ANOVA test. I'm going to do like yada, yada, yada. And then give a concluding sentence as to what you want to actually find or what you want to achieve. Now, the method section is perhaps, you know, kind of important, because that's how we know about reproducibility. You know, like if you made a logical mistake in your actual method section, there needs to be enough information for the reader to reproduce your study, basically, right? So even though Ken gathered the data for you, you should still elucidate, you know, how many observations do you have in your data set? Who are the units that you are actually sampling? So you have this many people of, you know, this particular group, this many of that group. You see how many units do you have? Who are the people you're studying, basically? Maybe it gives you some insight as to where the data came from. He could actually give you some additional insight there. You should state this as well. Even if he states it in his report, you should restate it yourself in your own words, like the data came from this. You have this many people in the study. You're trying to, you know, and within this many people, you have maybe this many males and females. You have, you know, whatever you're looking for. You have this many people in the treatment group, this many people in the control group. And then you're going to say, like, I'm going to do an ANOVA using R. You know, I'm going to do a Tukey's HSD. I'm going to do whatever. You should state that the inference you're going to do this. I'm going to do an ANOVA. I'm going to use the p-value of 0.05. You know, I'm going to compare these two groups or these 3 groups here. I'm going to check to see if the variants are equal. If they're equal, I'm going to use ANOVA. If they're not, I'm going to use Welch's test. So you need to be very explicit as to how you're going to determine which test you're going to use, what the criteria determine. So if, you know, if it's the case that the variants are equal, I'm going to use this. If not, I'm going to do that. The analysis and the results when you're going to actually explain what you saw, basically. Now, you're not going to give context as to why you actually, the conclusion is when you actually talk about what your analysis showed. But the analysis is you actually explaining the graphs and tables, basically. So, you know, you saw this effect, you know, you're going to explain what you saw clearly, but don't explain why you think that finding was true. So don't conflate explanation, or don't conflate presenting your results with giving justifications as to why your results came up that way. That's for the next section, basically. So just present your results clearly and make sure you elucidated, you contextualize, you know, all your data, but don't explain why you saw what you saw. That is for the conclusion part there. You're going to say, you know, based on the results section oh, we saw this, and then offer your opinions about why the results are like that in the context of your data, but also from a framework of like in general, basically. That's when you can be creative and say, well, earlier studies have shown this, I think that this is like this because of that. And you can really go past your data and give your own context, what you think you saw. That's when you want to actually be creative with your analysis, basically, right? So this is what he means by like, what does your analysis tell you about the problem? So be creative here, really give contextualized answers to your actual analysis, but don't explain what you saw. Don't explain why you think you saw what you saw in the section here. That's for the conclusions, right? So the one thing I want to point out to you guys before the class ends that, you could have a look here, obviously, because maybe a lot of papers kind of tell you what you should look at, but I want to show you guys the tables. This is something that is always kind of a bit of an issue for people, right? So how to present, for instance, your results, right? So please note that you have the descriptive statistics, right? Which is, he kind of gives you an example here. He does give you the descriptive statistics of what you saw in your thing. You saw 82% had this, you kind of describe what you saw, basically. You just literally describing what you saw in your data, basically. This is not inferential. Descriptive statistics is you actually using tables and figures to elucidate trends you saw in your data. The inference, well, you want to extrapolate past your data levels. There's two components to results sections. The descriptive statistics is to what your data actually showed. And then there's actually inferential. So even box plots are descriptive. So, but the ANOVA itself is inferential, basically, right? So keep this in mind. When the inferential statistics is actually the ANOVA, the cookies, the descriptive statistics, your box plots, whatever, describing proportions or percentages. Those are separate things, which should both go in your results section. But please notice that they're interweaving the tables inside the actual thing, right? So make sure you say from table one or refer to table one, we have this. Please look at table one. So, table one shows us this, figure one shows us that. So interweave it into your actual results. And notice that we actually clearly define, like and elucidate what each table is. So when you have a table here, you might actually put in the bottom your figure one, and you put an explanation that gives enough detail for the people to understand what it is you're actually trying to convey. So make sure that the figure always has a figure always has a context in the bottom of the thing, the page. It gives enough information so the reader can understand what you're actually trying to convey without having to scan the report itself, basically. Because that's the goal. You gave enough information so that the reader doesn't have to scan the report themselves to figure out what you're trying to say. And I wonder if he actually gave an example as to how to present a table, because that would be kind of cool. Let me see. Let me see. I don't think he does, but a table is kind of similar to a figure, except I think that the label's on the top, right? So let's have a double check and see, because I haven't written a report this year, so I don't want to do something wrong. Okay, so here's the PDF he uses to kind of go over the forms. I just want to see if the table, yeah. So that's what I thought. You see, unlike a figure, the table has the explanation on the top, right? So when you keep this in mind, but the figure will always have it at the bottom. So you see a figure always say figure one here. So this is something to keep in mind. The figure will always have the information at the bottom, right? But a table always has, table one. That's because you're going to obviously want to scan immediately what you're looking at in the table. You need to give context to the table right away to the actual table you put in your results, and that's why it's always at the top of the actual page, right? So I would certainly say make sure when you write your report to keep his PDF he gave you here in mind. It's going to be very helpful for you, and obviously go back and watch what I said here as to what you're looking for. I'm actually not grading the reports myself, but I would imagine that the grader who is actually grading this would be really thankful if you did, kind of follow this kind of ideas, because then it would make their job a lot easier to grade your work. Does anyone have any questions about this before we kind of dispense, I guess? So that's, I guess, pretty much it. And good luck with your reports. Hopefully it's fun to write them. You too. Have a great day.